1 point apiece. Okay, so you can kind of see on the answer key what I was after. The stoichiometry, or what relationship gives the stoichiometry of a chemical reaction. And I would rather have you say something about the balanced chemical equation, but so I took a variety of answers there. Question B, when we use the term aqueous, what do we mean? And we mean dissolved in water. A lot of times you'll see the word ionized associated with that, where water is the solvent. Number C, a gross error is that oops, or S blank, 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 error. Okay, so honestly, gross errors can generally be avoidable. And so give an example of a gross error. So I picked misreading the scale is an example of a gross error. Another gross error is where you literally accidentally spill part of your reaction solution. Okay, some loss is inherent, but that's not. Okay, so question E, which form, we talked about different ways of saying how concentrated a solution is, and one that is independent of temperature needs to be one that's independent of volume, basically. And so, of course, molality is, and we haven't talked about molality yet, but molarity is very dependent upon volume. It's moles per liter, but mass percent is not. So the best answer there, or a good answer there, would be weight percent is independent of temperature, something that doesn't have volume in it. F, if I tell you calcium chloride is the compound of interest, and I give you the formula, if you look for a metal, if there is a metal, then it must be an ionic compound. Of course, calcium is a metal. It's on this side of the JAG. Question G, in a titration, when we talk about the titrant, what are we talking about? And that is the solution of the burette. And H, one of the reasons that you don't always get back product-wise, what you think you should get back is this kind of ball together side, parallel, or competing reactions. And so I wanted you to try to tell me what you thought that meant. And so an example of that was when you guys were combining magnesium with oxygen to form magnesium oxide. And instead of combining with oxygen, it combined with nitrogen in the room. So, so that's one of those. The next page, these were each worth 2 points apiece. And the one up there is you're supposed to simplify the compound containing 9 carbons, 18 hydrogens, and 3 nitrogens. And of course, you can divide each of those by 3 and get 3, 6, and 1. So that's going from a molecular formula to an empirical formula. B, notice that they gave you the molar mass, 86.17 grams per mole for a compound, and you were supposed to give the molecular weight. And of course, the molecular weight is the same number, but different units, atomic mass units. For C, you might kind of recognize that sort of problem, where if you have something like magnesium bromide, and we'll be talking more about how you call it magnesium bromide, but MgBr2 ionizes or separates into 1 Mg, actually Mg2+, and 2 Br minuses. So if you were given the molarity of the ionic compound as 0.132 molar, then you could use a relationship 2 moles of Br minus for every 1 mole of MgBr2. So of course that gives you double the molarity of the bromide ion. The next one, so they went ahead and told you the molar mass is 112.2 grams per mole, and they gave you the repeating unit or the empirical formula as 1 carbon and 2 hydrogens, and wanted you to scale up what must then be the molecular formula of that compound. And this was the tail end of a problem that we worked, going from weight percent, for example, all the way through empirical formula to molecular formula. You can do this if this information is given. So basically, you find the weight of the repeating unit, 1 carbon and 2 hydrogens, that's 14.03, and you see how many repeating units of that are in that particular compound. So if you divide the 112.2 by 14.3, you get 8 repeating units. So scaling it up must be C8H16. So the next one, given the compound methane, 1 carbon and 4 hydrogens, basically focusing on the hydrogen, what is its weight percent. So there's a couple different ways to work that, and actually this is one of the few sections where you didn't have to show all of your work. But basically you need to have the mass of the hydrogen, 4 times 1.08, divided by the total mass, which in this case is 16.04 times 100 to get it parts per 100. Actually, you had a series of problems that were each worth 6 points. And if you find yourself thinking, now wait, this problem is easier than the other one that's worth 6 points, you're right. Okay, some of these were harder and some of these were easier. But they were all things that we talked about in class. So in this case, you were given the weight percent of carbon, hydrogen, and oxygen. You were supposed to come up with the empirical formula. So it's kind of like we talked about in class. If you take as your basis 100 grams, then that means that you have, over here, you have these masses of carbon, hydrogen, and oxygen. And then we can use the molar mass of those things to come up with relative moles of those things. Okay, so this is kind of my table form approach of this. And then to try to get it in, to get these in whole numbers, we can divide by the smallest number, which in this case is 1.972 moles. And notice that we end up with a kind of a threes-ish, 1/3-ish. So if we go ahead and take all those times 3, we end up with 8, 8, and 3 as relative moles of carbon, hydrogen, and oxygen. So that is the empirical formula. Was this one. And of them, honestly, this is probably one of the hardest. This actually is a dilution problem and then something on top of the dilution problem. So it tells you that you have a certain amount of stock solution, okay? It gives you information about the stock solution. It gives you its density and its weight percent. Okay, and it says that you are going to make a diluted solution, and it gives you information about the diluted solution. Specifically, you're going to have 75.0 milliliters of that diluted solution, and you know its molarity after you diluted it is 0.225 moles per liter ammonium chloride, NH4Cl. And it asks how many milliliters did you need to transfer to make that happen. So the way I did it, kind of, you see the headings on working the problem. First, I came up with the moles of ammonium chloride in the diluted solution using volume and molarity. Okay, so running around in that diluted solution, we must have 0.0169 moles of ammonium chloride. And then I pondered, how do we get moles from density and weight percent? Okay. So I knew that we were going to have to go from grams to moles. So here's the molar mass of the analyte, NH4Cl, 53.94 grams per mole. And then I just started setting it up. So this is all about the stock solution now. So I go from moles that I know needed to have been transferred, the 0.0169 moles of ammonium chloride. I use its molar mass to get to grams of ammonium chloride. And then the weight percent was given, 22.0 grams of ammonium chloride per 100 grams of solution. So that will give me the grams of solution. And then if I go ahead and knock in the density, which is 1.06 grams of solution per milliliter solution. So the transfer volume must have been 3.88 milliliters of solution. Yes, only worth 6 points. So the next one, relatively straightforward. When I graded your your lab write-ups, for those of you who did calculations and brought them took me up on that generous offer, this is kind of similar to that. So basically, kind of at the top there, you see that you're given the volume molarity of the HCl, you're given the volume of the Na2CO3, and asked to find the molarity of the Na2CO3. So you start with what you know most about, get moles of HCl from the volume and molarity, then you use the stoichiometry of 2 to 1 to get to the moles of the Na2CO3, and then once you have the moles, you divide it by the volume to get to the molarity. So this one was similar to burning, this one was similar to a combustion problem where you have carbon, hydrogen, and oxygen. But in this case, it's carbon, hydrogen, and nitrogen. Very similar approach, though. So underneath the thing we were combusting, I have the mass, the 1.297 grams. That's what we were combusting. We got the mass of carbon dioxide. Of course, we get moles of carbon from that. And the mass of H2O, we can get moles of hydrogen from that. So actually, that's kind of what you see me do right away. I knock out the molar mass of CO2 and the molar mass of H2O. By the way, there were some of you, and you know who you were, who did not put those molar mass calculations. I kind of glossed over it this time, but I reserve the right to return to my docking you a point here or there, which kind of stinks. So make sure that you write out your molar masses. So I get the, like I said, the moles of carbon from the carbon dioxide, moles of hydrogen from the water. So the deal here, though, is notice I went ahead and knocked out the mass of carbon and the mass of hydrogen from the moles of carbon and the moles of hydrogen. Because I'm going to need that mass of carbon, mass of hydrogen. There at the end, or actually the next section, you have me get to the nitrogen now. So we knew how much we combusted. We knew that we combusted 1.297 grams. And now we know the mass of the carbon, we know the mass of the hydrogen, and by difference we can knock out the mass of the nitrogen. So once we have mass of nitrogen, we can finally go ahead and use the molar mass of nitrogen, 14.01 grams per mole, to get to the moles of nitrogen. And so then down here is my kind of little table thing. From up above, now we have the moles of carbon, hydrogen, nitrogen. We're ready to go ahead and divide by the moles that are the fewest amount, it's the nitrogen. Notice that with this first division, we end up with kind of a halvesy or 0.5 sort of deal. So I have one more column to go ahead and multiply by 2. So relative moles of carbon, hydrogen, and nitrogen are 3, 10, and 2 respectively. The next one was 2 parts. Each were worth 6 points apiece. In the first part, you needed to, given those masses of those 2 reactants, which one is in limited supply? And of course, actually, it's the one that's in limited supply that you're going to answer part B with. So there's different ways to do this, and you can kind of see how I did it. I went ahead and you need to show the molar mass of getting the TiO2, molar mass of BRF3, convert the grams to moles, and you can see the half relative number of moles over there on the right. And so I went ahead and took a ratio of, in this case, the BRF3 to the TiO2, the half ratio, and the need ratio, of course, came from the coefficients in the balanced chemical equation. Okay, so the fact that with regard to the BRF3, that you only have 0.688, but you need 1.33, that means we can say with regard to the BRF3 that it's in limited supply. Okay, because we only have so much, then we need more than that. So that was actually then the reactant that you did this next part on. So then it said, all right, so now you've identified what's in excess. So what's in excess is the TiO2. So the question related to the excess reactant is how much will you have left? So to know how much you have left, you have to use the limited reactant, which is the BRF3, to see how much you will react. Okay, so I didn't backtrack to grams and molar mass, but simply from above, the number of moles of the BRF3 was 0.0215. It reacts in a 3 to 4 relationship with the TiO2. That means then I can tack on the molar mass of the TiO2 to get to grams. So that means that 1.29 grams of the amount that was given in excess is going to react. So to get the amount that was unreacted, of course, we take the initial amount, 2.50, and from that subtract the 1.29 to get the amount that will remain. Blank page. Okay, so like I